Hello all, this is Mr. G and this is our warm-up for today's lesson. So pause the video right here, give this problem a shot, come back when you think you have an answer. We're going over in 3, 2, 1, let's go. We've got to find the local extrema of the function f of x equals 1 over 20 times x plus 1 to the third power times x minus 5 plus 4. Well, first we need to know what local extrema are. Local extrema are essentially relative maximums and relative minimums. So what we have to do is plug this function into a graphing calculator by hitting y equals, then we do 1 divided by 20, parentheses x plus 1, hit the caret button to get the power, then hit the power of 3. Let's hit right to get out of the exponent. Open a new parentheses, x minus 5 plus 4. Let me double check that. Plus 4 minus 5. Looks like I got it. I hit graph. And we get this function. So I don't see both relative maximums and relative minimums. I only see one. There are no relative maximums. So for relative maximums, I'm just going to say none. But there is a relative minimum. If I can draw sort of what the graph looks like, it looks something like this. The relative minimum is going to be right here. Right? Now, some of you might have been looking at this point and saying, well, wait a minute, is that going to be a maximum or a minimum? It's sort of like swiveling. That's not a maximum or a minimum because, like, the points on this side are smaller than it, and the points on this side are bigger than it. So in that section, that point is not a relative maximum or minimum. We just have to find that point right there for our relative minimum. So I go to second, calculate, go to minimum, and then we've got to do our left bound, right bound. So I'm going to move a little bit closer to the minimum, hit enter. Then I go to the right, past it for right bound, hit enter, and enter one more time. And let's see what we get. We get Okay, some weird rounding stuff here. It says 3.5 and a whole bunch of zeros. We're just going to say that's 3.5. And our y value is negative 2.83 in round 2, negative 2.83. So that's our, not just a relative minimum, actually, that is the absolute minimum of this function, because there's no point in this function lower than that point. So there you go. There are the local extrema, and really just absolute extrema of that function. Here's our objective, though. We're doing chapter 4, section 3. After today, we should be able to interpret quadratic functions that represent projectile motion. Projectile motion is something you'll talk a lot about when you get to physics, or if you're already taking physics, so hopefully that sounds sort of familiar. When you're in physics, you do things like, okay, here's the projectile motion, like we're throwing a ball at this velocity, at this angle, and you actually come up with the equation. We're not going to do anything that advanced. We're going to just do some basic projectile motion stuff, where we're looking at, okay, so here's the path of a projectile, maybe it's thrown like that, and say, okay, so when is it going to hit the ground? When is it going to be at its highest point? What was its starting height? We're going to answer questions like that based off an equation that's already given to us. So basic projectile motion pretty much looks like this. We have something, we throw it, and it lands on the ground, or someone catches it, or whatever. It eventually hits something. Now, what we're going to be talking about is we're going to be comparing the time that goes on. So the x value, the independent variable, will be time, how much time has passed, and the y value, the dependent variable, will be height. That usually time is in seconds. Height can vary. Sometimes it's in feet, sometimes it's in meters. It depends on the problem. Now, before we actually get into a problem, we need to understand, okay, so what are these points going to be meaning? All right. Actually, before we even talk about that, there's one thing I forgot to talk about. This picture right here should look pretty familiar. You should be looking at that and thinking, wait, that sort of looks like a function I remember. That sort of looks like a parabola. Because if I sort of extended it, like in this direction, and then so we kept on going and then kept on going in that direction, we get a concave down parabola. So projectile motion is essentially a quadratic problem. It just looks, I don't want to say this. It's just put into the context of a real world situation. And that's something you want to make sure you're getting better at as you progress in your mathematical career. You want to be able to look at a graph and say, oh, that's a parabola, or that's a linear function, or that's an absolute value function, or that's an exponential function. You want to be able to do that as you're growing and growing in your mathematical careers, like I said. All right, so what do these points actually mean? We've got a few ordered pairs here. We've got 0, 7, 1.2, 8.4, 3.075, and 4.14, 0. So what's going on with these points? So let's just sort of go from left to right. So this point, 0, 7, that essentially means, okay, the x value is 0, and that will give us a y value of 7. Well, wait a minute, the x values are time, and the y values are height. So that means at a time of 0 seconds, at the exact instant we start our stopwatch for this projectile motion problem, that means we're at a starting height of 7 feet. So that means at 0 seconds, we're at 7 feet. Similarly, right here, okay, we've got 1.2 and 8.4. So that means at 1.2 seconds, our projectile, whether it's a ball or a rocket or whatever we're throwing here, a potato out of a potato launcher, whatever it is, after 1.2 seconds, it's 8.4 feet in the air. Okay, but down here, at 3.07 seconds, it's 5 feet in the air. And down here, at 4.14 seconds, it's 0 feet in the air. So that means it's hit the ground. Now, I can sort of feel through the magic of the internet world, I can see some of you looking at this screen being like, okay, we get it. This is not that big a deal. But what we just talked about, the X's and the Y's and what they represent, time and height, that's the most important part of these projectile motion problems. If you really understand that, the rest is easy. If you only sort of understand it, then you're going to be kind of confused through this whole lesson. So make sure you always keep track of what your X values are and what your Y values are. The last thing we're going to talk about on this slide before we actually get to some examples is sort of attaching some Algebra 2 vocab to this basic projectile motion problem. So this point right here, we have a name for that point. We call that the y-intercept. So the starting height, or the starting point, we should say, is always the y-intercept because, the y-intercept always has an x value of 0. And for the vast majority of basic projectile motion problems, time always starts at 0. There might be some exceptions when you get into more complicated physics problems, but for our purposes, we're always going to start at a time of 0, which makes the y-intercept always our starting height. Then this point right here is the vertex. That's the maximum value here. Since it's concave down, the vertex is the maximum value. And then this point right here is the real root, the 0, the x-intercept. And this point right here, well, we don't really have a special name for it. It's just another point on the parabola or on this projectile motion problem, all right? So that's really what we're going to be doing today, sort of applying, okay, what does x mean? What does y mean in this context? And applying our Algebra 2 vocab to these problems. So let's take a look at example 1. It says the height of a miniature rocket in feet can be modeled using the function h of t equals negative 16t squared plus 158t plus 2, where t is the time in seconds after the rocket is launched. Will the rocket reach a height of 350 feet? Answer this question without the aid of a graphing calculator. So when it says without the aid of a graphing calculator, we can still use the graphing calculator to get out of there. If we need to do like 2 times 8 or something like that, not that we'd have to do that in our head. But like we can use basic functions here, like addition, multiplication, exponents. We just can't use our y equals or any other graphing functions of this graphing calculator. All right, so at least when I look at this problem, the first thing I think is, all right, I'm a little confused. I'm sort of always overwhelmed the first time I read through a paragraph. So my first thought is, okay, what are they asking me? So they're asking, will the rocket reach a height of 350 feet? That's what we have to answer. And then the most important clue they're giving us, because remember, in any math problem, there's always clues, no matter how complicated it looks. The big clue they're giving us is that equation. So I'm going to rewrite that. H of t equals negative 16t squared plus 158t plus 2. Now, don't get thrown off that we've got t's and h's instead of like an f of x and an x. We can treat these the same way. H of t, it's just like f of x, and t, it's just like x. So we've got a quadratic here, and it's saying, will the rocket reach a height of 350 feet? So basically what they're asking us, I don't want to say this, there's a few different ways to do this problem. One way, which I'm actually not going to go through, but it is a possible way, so I want to sort of talk about it a little bit. You can take this 350 feet and plug it in for the height. We could plug it in for h of t. So it would be 350 equals negative 16t squared plus, and we just copy the rest of it. And then we could just solve that and see if we get any real solutions. If we get a real solution, that means that this expression right here will be able to get us to a value of 350. So that's one way to do it. I want to do it a different way, though. What they're really asking us is about the maximum height of our projectile. It's saying, okay, will it reach a height of 350 feet? So if we can find our maximum height, then that's going to, how do I want to say this? If we can find the maximum height, that will tell us whether we're going to get to 350 feet or not. So let's draw, again, about what this is going to look like. So the projectile motion problem is going to look something like this. So our maximum height is this point right here. So really, this is a vertex problem. They're asking us for the vertex. Now we know how to do that on the graphing calculator. Hopefully you remember how to do that by hand. So pause the video right here. I want you to think of an answer. Okay, how would I start finding the vertex of a quadratic equation by hand without a graphing calculator? I'm going to give you the answer in 3, 2, 1. The answer is we use negative b over 2a. Negative b over 2a. That will give us the x-coordinate of the vertex. So let's see, that would be negative 158, all divided by 2 times negative 16. Now I'm going to plug this right into a calculator. It said we can't use a graphing calculator, but I'm not going to graph anything. So negative 158 divided by, and in parentheses, 2 times negative 16. And we hit enter, and I get 4.9375. I'm actually not going to round that. I'm going to leave it with all those decimal places because I only like to round at the very end of a problem. Okay, so that's the x-coordinate of our vertex. So that means we're going to reach our maximum height after 4.9375. It's seconds, correct? It's the time in seconds. Yeah, time in seconds. So at about 5 seconds, or a little bit less than 5 seconds, we're going to hit our maximum height. But we still have to find out what the maximum height is. We have to find the y-coordinate of the vertex. And to do that, we just take our x value and plug it in. I'm going to do this straight in the calculator. So let me scroll up so I can see my function a little bit better. So it's negative 16, parentheses for multiplication. I type in my time, which is 4.9375, close parentheses, square it, plus 158 times 4.9375. Oh, I missed my parentheses there. So if I just hit my parentheses, it's going to sort of overwrite that 4, but I'm going to hit second insert, INS is on the delete button, and then I can hit the parentheses and it just inserts it there. So that's a nice little trick, so I don't have to retype all that. Let me check the rest of my typing. 1.158, okay. Now let's go over and close that parentheses, and then we add 2. I'm going to double check I typed this correctly. So it's plus 2, 158 times 4.9375, good. And then negative 16 times 4.9375 squared. Let's hit enter and see what we get. 392.0625. 392.0625. That's our vertex. So that's not our answer though. If we just say, oh, 392.0625 feet, that's going to be an incorrect response because they didn't ask us what the maximum height is. They said, will it reach a height of 350 feet? And okay, if it's getting all the way to 392, then it's definitely going to get above 350, or it's going to hit 350 and then get above it. So the answer is yes, this rocket will reach a height of 350 and then even go past it. All right, so that's example 1. Let's take a look at example 2. It says the football is thrown and its height with respect to time can be represented with the function h of t equals negative 16t squared plus 19t plus 5. And it does not say we can't use a graphing calculator. So that means we're going to be allowed to use our y equals function. So that's going to make this problem hopefully a lot quicker than the last one we did. So you don't have to do this, but I always like to sort of at least draw my picture, or at least imagine it. So the projectile motion is going to look something like that. Now we got to find this football starting height. We got to figure out when did the football hit the ground and answer what was the football's maximum height. So what is the football starting height? If you really understand what we're doing here, you don't need to use anything like, how do I want to say this? You don't have to use a graphing calculator. You don't have to do it by hand. You should just be able to see the answer. Because remember, the starting height is always the y-intercept. And that's going to be the starting height. And the y-intercept, if you look, is our c value. It's 5. Now, if you didn't remember that, that c is always the y-intercept, there's another really easy way to get to this. You remember, okay, so this is going to be our starting height or our starting point, and we know it's going to be 0 something. If the x value is 0, just plug in 0. So that would be h of 0 equals, well, let's see, negative 16 times 0 squared, that would just be 0, plus 19 times 0 is 0, plus 5. So you can quickly see that it's just going to be 5. So that's a couple little tricks to get to the y-intercept in case you forget that it's always the c value. Get rid of that as well. Okay. Now it said when does the football hit the ground? Here I'm actually going to plug it into my calculator. So I'm going to clear this out. And it's negative 16x squared plus 19x plus 5. Even though we see t's in our original equation, you want to make sure you're still hitting the x button on your graphing calculator. The calculator doesn't understand what t is. You have to use x. Got to use x. Now I'm going to graph. Let's see what we're looking at. That's kind of a weird picture, but we can see most of it, so I'm just going to leave it as it is. All right, so when did the football hit the ground? Well, that's going to be this point right here. So we have to apply our Algebra 2 vocab to make sure we understand what point we're looking for. That point is a real root. So we're looking for the real root of this function. To do that, we hit second, calculate, and we go to 0. Remember, real root, 0, x-intercept, those things all mean the same thing. I'm going to hit 2. Now we have to do our left bound, right bound, so I'm going to try and get close to our real root. Again, we're looking for this real root right there that I'm sort of surrounding. That points to the left of it, then I go to the right of it, hit enter. Enter one more time to guess, and we get 1.41 it rounds to, 1.41, and then the y value is 1e negative 12. Remember, it says e and a negative number, that's just a 0. That's just a 0. So the question is, when did the football hit the ground? So we don't want to give it the full order pair. We don't want to give it 1.41 comma 0. It's just asking for the time for when it hit it. And the time is t. That's our first value. That's the x value, essentially. So it's going to be after 1.41 seconds. That's when it's going to hit the ground. All right, now moving on to C, what was the football's maximum height? Okay, so the maximum height, that's the vertex. So this is a vertex problem. So we're looking for the maximum. So I go to second, calculate, maximum is number 4. Now we can't actually see the vertex. We can't see the maximum value on our calculator, but that's okay. That's okay. I'm just going to sort of move to my cursor. Okay, I know that's going to be to the left of it. I hit enter. Then I'm going to move to the right of it. I can't quite see my cursor. Let me keep going. There we go. There's my cursor. I know that's to the right of it, so I hit enter. Then enter one more time. And we get, 0.59 it rounds to, so 0.59. And what's the y value? 10.64. Let's rewrite this so we can actually read it. Let's try that. So it's 0.59. And what was it? 10.64. But again, we don't want both of those numbers. It's asking what was the football's maximum height. So that's our height. That's the y value. So we want 10.64. What was it? Feet. It doesn't say what units are. Football's thrown its height with respect to time can be. I'm just going to assume it's feet. I'm going to assume it's feet. All right. So that's the answer to that problem. Hopefully you see that this is a lot quicker with the graphing calculator, as long as you understand what you're looking for. If you don't see things like, the starting height, I know that's the y-intercept. If you don't see, when did it hit the ground, that's a real root. If you don't see, the maximum height, that's the vertex. We're looking for a vertex there. If you don't make those connections, then these problems become really, really complicated. But if you make those connections and you can sort of connect this projectile motion with our Algebra 2 vocab, then this is probably going to look like the same exact problems we've been doing, because essentially the math is all the same. We're just putting it in context now. All right, so example 3, I want you to try this one on your own. I'm going to show the answers in 3, 2, 1, let's go. It says a baseball is thrown from 7 feet above the ground with a vertical velocity of 7.78 feet per second. Its height above the ground in feet with respect to time in seconds can be modeled with the function h of t equals negative 16t squared plus 77.78 t plus 7. Now, honestly, the only thing I care about is this. Like all that other stuff, that's just flavor text as far as I'm concerned. So I'm not even going to look at that. I'm just going to go to y equals, clear this out, and enter my new function. It's negative 16x squared plus 77.78x plus 7. I'm just going to double check I typed that incorrectly. 77.78 and negative 16. Okay, good. Or x squared, I should say. We graph it. Ooh, that's kind of ugly. So I can't really see most of the graph. So basically what's happening, I'm just going to draw this here. It's going up like really, really close to the y-axis. Then we can't really see where it's turning around. Then it's coming back just for the very, very bottom. But that's okay. That's okay. We can still use the graphing calculator to find our answers. So first I'm going to show you all 3 answers. Then I'm going to go back and show you how I got to them. So when will the baseball hit the ground? After 4.95 seconds. What is the baseball's maximum height? 101.53 feet. And when will the baseball reach its maximum height? 2.43 seconds. So now let's go back and figure out how we did that. So that way you can sort of jump to the part of video that you need if you need to see any of these, if you need to see me find any of those answers. All right, so when will the baseball hit the ground? So we're looking for a real root there because that's how projectile motion works. When it's hitting the ground, that's a real root. It's hitting the x-axis. So I'm going to hit second calculate 0. Now, I'm not going to be able to see my cursor for a lot of this, so I'm going to keep a close eye on my x and y values on the calculator. So my y value is 37, 50, 61, 71, 80, 87, 93, 97, 100, 101, still 101, and now it's 99. So now I know I'm coming back down the parabola. Okay, so 92, 79, 59, 48, 35. Someday it'll show up. There we go. And we finally got our cursor. Since if you weren't keeping track of the y values, sometimes you're just sort of hitting left and right, sort of hoping you're going to see your cursor. So keep an eye on the x's and y's that are on your screen. That'll keep track, or at least tell you where you are and where your cursor is heading. All right, so that is to the left of my real root. I hit enter. I hit right one more time, and we're off the screen already, but I hit right, so I know I'm to the right of my real root. I hit enter, then enter one more time, and we get the point 4.94. Let me write this down. So we got the point 4.95 it rounds to, and 1 e negative 11, we know that's just a 0. So that's how we got 4.95 seconds. The x value is the time. So make that look like a 4. That's a little better. Okay, move on to B and show you how I got this answer. What is the baseball's maximum height? That means we're looking for the maximum, the vertex. I hit second, calculate, maximum is 4. Now, again, I'm going to keep track of my y values to make sure I'm getting past the part where, or past the highest point. So y is 48. I think it was like 100 or something like that. I'm at 96, 99, 101, 101. Okay, 100. Now I'm coming back down. 97, 93, 87. So at 87, I know I'm to the left of my maximum. I'm going to hit enter. Now I need to go to the right. So now I need to go back to the right and past the highest point. So 97, 100, 101, 101, 99. Okay, I'm going to go a few more just to be safe. There's 86. That's sort of nice and symmetrical. One was 86, one was 87. I hit enter. It doesn't. The numbers don't have to be that close. That was just sort of a lucky coincidence. Hit enter one more time, and we get the point. Let's see, what is that? 2.43 and 101.5. 53 it rounds to. Sounds like a radio station. And that's how we got 101.53 feet, because we wanted the maximum height, which is the y value. Last but not least, we're going over how do we get the answer for number C. Oh, when will the baseball reach its maximum height? Okay, so then we use the same ordered pair, the vertex, 2.43 and 101.53, and this time it's asking for when. So that's when we have to put 2.43 seconds. So you always have to pay very close attention to what they're asking you, especially with the maximum, because the maximum, they could be saying, what is the maximum height, or when did we get to that maximum height? So make sure you're always sort of reading your questions carefully so you understand what they're asking for. Okay, hopefully that all made sense. If you have questions, as always, let me know. Enjoy the rest of your day.